Welcome to the Ready Academy. Tools for teaching, tools for learning, tools for life. In this video book, we cover simple machines. This content was produced with AI assistance and reviewed by a human instructor. We'll continue with the lever. Law of the lever from torque balance. A worker can lever up a 500-kilogram boulder with one arm, yet cannot lift even a tenth of that weight directly. The question is not whether this works, it obviously does. The question is why, and by exactly how much. The answer lives in torque, the rotational tendency of a force about a fixed pivot point. For any force acting on a lever, torque is the product of the force and the perpendicular distance from the pivot to the line of action of that force, a distance called the lever arm. Equation 3.1. Torque tau equals force F times the perpendicular length of the lever arm L. Torque is measured in Newton meters or foot-pounds. The torque grows with either a larger force or a longer lever arm. A lever is in rotational equilibrium when the clockwise torques exactly cancel the counterclockwise torques, the same condition that keeps a balanced seesaw horizontal. Setting effort torque equal to load torque gives the equation Archimedes proved in On the Equilibrium of Planes over 2,300 years ago. Equation 3.2. Effort force times effort arm length equals resistance force times resistance arm length. This is the law of the lever. When the lever is still, the two torques cancel exactly. Every lever from a seesaw to a crowbar is holding still for this reason. Figure 3.1. A horizontal beam balanced on a triangular fulcrum with a small figure on the long left side and a heavy stone on the short right side, showing a lever in rotational equilibrium. Labeled arrows mark the effort force on the left arm at distance LE from the fulcrum and the resistance force on the right at distance LR, with a curved pivot arrow at the fulcrum and a dashed horizontal line showing the beam stationary when the two torques balance. Rearranging this equation gives the ideal mechanical advantage formula for any lever. Equation 3.3. The ideal mechanical advantage of a lever equals the effort arm length divided by the load arm length. This is the maximum force advantage possible. The force multiplication is set entirely by where you place the fulcrum. This ratio is the quantitative content of Archimedes' famous boast. Once you know the lever arm lengths, you know the force multiplication exactly. Animation 3.1. A lever beam rests horizontal on a fixed fulcrum, holding a 100 Newton load 1 meter to the right. The effort weight sits 5 meters to the left. The effort arm is 5 times the load arm, giving an ideal mechanical advantage of 5. The effort weight slides inward along the beam. As the effort arm shortens, the effort force rises to keep the torques equal and the beam level. At each position, the beam stays horizontal. Every configuration is a new static equilibrium. The effort weight slides back outward to 5 meters. The effort force falls, the torques stay balanced, and the beam remains level throughout. The ideal mechanical advantage returns to 5, and the effort force returns to 20 newtons. The fulcrum does not merely sit there. It pushes in an equal and opposite direction with a reaction force equal to the vector sum of both applied forces. Equation 3.4. The force at the fulcrum equals the vector sum of the effort force and the resistance force. The fulcrum keeps the lever in place while allowing it to rotate. A lever is in static equilibrium when two conditions hold simultaneously. The net force on the beam is 0, and the net torque about any point is 0. The arm lengths LE and LR describe geometry, where the forces act relative to the fulcrum. Section 2 established work as the product of force and distance, conserved exactly by any ideal, frictionless machine. The lever inherits that law directly. However, the distances dE and dR describe motion, how far each force moves through an arc when the beam rotates through a small angle. Thus, for a lever, the effort force does work by acting through the effort arc distance, and that work is delivered to the load through the load arc distance. Figure 3.2. A lever beam is drawn in its horizontal resting position, with straight lines from the fulcrum out to the effort point, and the load point marking the perpendicular arm lengths LE and LR that enter the torque equation. The same beam is shown rotated through a small angle, with curved arrows tracing the arc each end sweeps through, a longer arc DE at the effort end, and a shorter arc DR at the load end, showing that these travel distances, not the arm lengths, are what enter the work calculation. Equation 3.5. For an ideal, frictionless lever, effort force times effort distance equals resistance force times load distance. The lever conserves work. What you gain in force you give back in distance, exactly. Because the beam is rigid, both ends sweep through the same small angle when it rotates, so the arc distances scale with the arm lengths. The effort end travels 5 times farther than the load end, just as its arm is 5 times longer. Archimedes understood that any load, however large, yields to an effort small enough, provided the ratio of arm lengths is large enough and the fulcrum can handle the forces. The lever does not create force. It trades distance for force. What would life be like without levers? 3 classes of levers. All levers obey the same law, yet a crowbar multiplies force enormously while a pair of tweezers throws force away. Both are levers. The difference is which of the 3 key points, fulcrum, load, and effort, sits between the other 2. That determines whether force is gained, lost, or unchanged. First-class levers have the fulcrum in the middle. Their ideal mechanical advantage can be greater than, equal to, or less than 1 depending on fulcrum placement. Examples include the seesaw, crowbar, scissors, and claw hammer. Second-class levers have the load in the middle, so the ideal mechanical advantage is always greater than 1. The wheelbarrow, nutcracker, and bottle opener all work this way. And finally, third-class levers have the effort in the middle, giving an ideal mechanical advantage always less than 1. You trade force for speed and reach. Tweezers, a fishing rod, and the forearm during a bicep curl all belong here. The human body relies almost entirely on third-class levers. The elbow, the knee, the jaw, sacrificing force multiplication for the speed and range of motion that muscles alone cannot deliver. Figure 3.3. 3 side-by-side diagrams show the 3 lever classes. The left panel is a first-class lever with the triangular fulcrum at the center of a horizontal beam, effort pressing down on the right side, load lifted on the left. The center panel shows a second-class lever as a wheelbarrow. The wheel axle is the fulcrum at the right end. A load of bricks sits in the middle, and the worker lifts upward at the handles on the left. The right panel shows a third-class lever as a human forearm. The elbow joint is the fulcrum. The biceps tendon applies effort partway down the forearm, and a dumbbell at the wrist is the load. Crowbar. A 1.2-meter crowbar is used to lift a 900-Newton rock. The fulcrum is placed 0.2 meters from the rock. The worker pushes down on the far end. Assuming the bar is ideal, find A, the lever arms, B, the IMA, C, the effort force, and D, how far the worker's hand moves when the rock sweeps 5 centimeters. Step 1. Find the lever arms. The load arm is the distance from the fulcrum to the rock. The effort arm is the remaining length of the bar. The load arm LR is 0.2 meters. The effort arm LE is 1.2 minus 0.2, giving 1.0 meters. Step 2. Calculate the IMA using equation 3.3. Divide the effort arm by the load arm. IMA equals LE divided by LR. 1.0 divided by 0.2 equals 5. Step 3. Find the effort force. Apply the law of the lever and solve for the effort force. Effort force equals Fr times Lr divided by Le. 900 times 0.2 divided by 1.0 equals 180 newtons. An IMA of 5 cuts the required force to 1/5 of the load. 180 newtons instead of 900. Step 4. Distance trade-off. The IMA also tells us exactly how the distances scale. The effort distance of travel equals IMA times the load distance of travel. 5 times 5 centimeters equals 25 centimeters. When the rock sweeps 5 centimeters, the worker's hand sweeps 25 centimeters. Force is multiplied by 5, distance is divided by 5, and work is exactly conserved. LR equals 0.2 meters, LE equals 1.0 meters, IMA equals 5.0, effort equals 180 newtons. Hand travels 25 centimeters for every 5 centimeters of rock travel. Seesaw balance. A child of mass 30 kilograms sits 1.8 meters from the center of a seesaw. Where must a 50-kilogram child sit to balance her? Step 1. Write the law of the lever. The torque from each child's weight must balance across the fulcrum. Force 1 times distance 1 equals force 2 times distance 2. Step 2. Each child's weight is her mass times the gravitational acceleration g. Mass 1 times g times distance 1 equals mass 2 times g times distance 2. Step 3. G appears on both sides of the equation, so it cancels, leaving mass and distance alone. Mass 1 times distance 1 equals mass 2 times distance 2. Step 4. Substitute the known masses and distance, then solve for the unknown distance L2. L2 equals 30 times 1.8 divided by 50, which equals 1.08 meters. The heavier child must sit closer to the center. Her greater weight is compensated by a shorter lever arm so that the torques balance. The 50-kilogram child must sit 1.08 meters from the center to balance the 30-kilogram child sitting 1.8 meters away. Wheelbarrow. A wheelbarrow is loaded with 90 kilograms of soil. The center of the load is 0.4 meters from the wheel axle. The worker lifts the handles 1.2 meters from the axle. What lifting force must the worker apply at the handles? Step 1. Find the load force. Convert mass to weight using gravitational acceleration. The load force equals 90 kilograms times 9.81 meters per second squared, approximately 883 newtons. Step 2. Find the IMA. The wheel axle is the fulcrum, the load arm is 0.4 meters, and the effort arm is 1.2 meters. IMA equals 1.2 divided by 0.4, which equals 3.0. Step 3. Find the effort force. Divide the load force by the IMA. Effort force equals 883 divided by 3, approximately 294 newtons. Two adult arms can easily supply 294 newtons upward. Lifting 883 newtons straight off the ground is beyond most people. IMA equals 3.0. The worker applies about 294 newtons, 1/3 of the 883 newton load, to lift and move the wheelbarrow. Claw hammer. A claw hammer 30 centimeters long is used as a first-class lever to pull a nail. The nail sits 4 centimeters from the pivot point. You pull on the handle 28 centimeters from the pivot. Find A. the IMA, and B. the force the claw applies to the nail if you pull with 80 newtons. Pause the video now and give it a try. Forearm lever. You hold a 5 kilogram dumbbell in your hand, 32 centimeters from your elbow joint. Your biceps tendon attaches to the forearm bone 4 centimeters from the elbow. Treating the forearm as a third-class lever, find A. the IMA, and B. the tension in the biceps tendon needed to hold the weight stationary. Pause the video now and work it through. Scissors. A pair of scissors has blades 6 centimeters long and handles 8 centimeters long, both measured from the central pivot. You squeeze with 30 newtons at the center of each handle. What maximum cutting force appears at the tip of each blade? Pause the video and see what you find. A first-class lever can have an IMA greater than 1, equal to 1, or less than 1, depending on where the fulcrum sits. Sketch one example of each, same lever, 3 fulcrum positions, and describe a real tool that corresponds to each case. That wraps up the lever. Next up, Section 4, the wheel and axle. If you found this helpful, like and subscribe, and support the channel.